Divide and conquer partitions. After the break taken in the last chapter, it is time we returned to our basic enumeration problems. In chapter 3, we were mainly concerned about the lists of objects, distinct or not, with repetitions as allowed or not, and with the order of the elements on the list being relevant or not. In this chapter, we will go one step further by considering distribution problems. We will distribute an object's balls into K boxes and ask in how many ways this can be done. Compositions. Let us assume we want to give away 20 identical balls to 4 children, Alice, Bob, Charlie, and Dennis. As the balls are identical, what matters is how many balls each child will get. So if we want to know the number of ways we can give away these balls, we simply have to note the number of ways to write 20 as the sum of 4 non-negative integers. Clearly, the order of the integers will matter. That is, 1 plus 6 plus 8 plus 5 does not correspond to the same way of distributing the balls as 6 plus 1 plus 5 plus 8. Indeed, in the first case, Alice only gets one ball, and in the second, she gets 6. Definition 5.1. A sequence A1, A2, A3 until AK of integers fulfilling AI which is greater than or equals to 0 for all I, and A1 plus A2 plus A3 and so on plus AK is equals to n is called a weak composition of n. If in addition the AI are positive for all I which is in K braces, then the sequence A1, A2, A3 until AK is called a composition of n. Theorem 5.2. For all positive integers n and k, the number of weak compositions of n into k parts is n plus k minus 1 choose k minus 1, which is equals to n plus k minus 1 choose n. Proof. The problem is certainly equivalent to counting the number of ways of putting n identical balls into k different boxes. Place the k boxes in a line, then place the balls in them in some way and align them in the middle of the boxes. This creates a long line consisting of n balls and k-1 walls separating the k boxes from each other. Note that simply knowing in which order the n identical balls and the k-1 separating walls follow each other is the same as knowing the number of balls in each box. So our task is reduced to finding the number of ways to permute the multiset consisting of n balls and k-1 walls. Theorem 3.21 tells us that this number is n plus k minus 1 factorial divided by n factorial times k minus 1 factorial. What if a grandparent insists on giving at least one ball to each child? The problem is not any harder. First, we can give one ball to each child, then give away the remaining 16 balls to the 4 children in any of 16 plus 4 minus 1, choose 4 minus 1, which is equal to 19, choose 3 ways. The generalization of this argument to n balls and k children is the following statement. Corollary 5.3. For all positive integers n and k, the number of compositions of n into k parts is n-1, choose k-1. How about the number of all compositions, that is, the number of compositions of n into any number of parts? Clearly, this question only makes real sense for compositions, not for weak compositions. Indeed, if 0 is allowed to be a part, then any number of zeros can be appended to the end of any composition. Therefore, any positive integer n has infinitely many compositions. For compositions, however, the question has a remarkably compact answer. Corollary 5.4. For all positive integers n, the number of all compositions of n is 2 to the n-1. Proof. A composition of n will have at least 1 and at the most n parts. So, the total number of compositions of n is the summations of n-1 choose k-1, summing with starting k equals to 1 to k equals to n, which is equals to 2 to the n-1. Indeed, the left-hand side is the number of all subsets of n-1, first enumerated by their size k, and then summed over k, which is in n braces. The reader is hopefully thinking right now that such a nice closed result, 2 to the n-1, must have an alternative explanation, one that really explains why the result is the power of 2. Such a proof indeed exists, and we provide it below. Proof of corollary 5.4. We prove the statement by induction on n. For n equals to 1, the statement is true as the integer 1 has 1 composition. Now assume that the statement is true for n and take all 2 to the n minus 1 compositions of n. For each such composition C, we will define the 2 different compositions of n plus 1. First, add 1 to the first element of C. This way, we get a composition of n plus 1 with the first element is at least 2. Second, take C and write an additional 1 to its front. This way, we get a composition of n plus 1 with the first element 1. It is clear that different compositions of n lead to different compositions of n plus 1 this way. Each decomposition of n plus 1 can be obtained in exactly one of these two ways. Therefore, it follows that n plus 1 has twice as many compositions as n, which was to be proved.